All right, we're starting out jumping over to chapter 3, and we'll start with the first section here, the water cycle and carbon species. The reason for that is that we are doing the water lab first, so we need to discuss the water chemistry and water in the environment before we get to that lab. So if you don't have the book yet, that's all right. What I've done is pulled the figures out of this chapter, and if you do have the book, you'll see that the author tends to heavily rely on figures, and then he has each section as a description of that figure anyway. So we'll just walk through it in those terms. In the first figure, he shows the hydrologic cycle, and this is important to understand where our water is at any given point in the cycle on Earth. So if we look in terms of starting with just up here with atmospheric circulation, okay, what we're doing is we're starting with our reservoir. So we've got our ocean reservoir, that's where most of our water is, and we'll talk about that in a minute. The water from this source, not just the ocean, but from anywhere, we get evaporation coming off. This is most of where we get our evaporation, circulates through the atmosphere, and then it's atmospheric precipitation that can reach critical mass and fall as rain. It can come down as snow. We can have respiration going on where this moisture is taken up by other sources, oceans, rivers, soil, vegetation, and then cycles back through. So as this moisture hits land, in the form of ice or rain, we get surface runoff, which picks up material from the surface, dissolved ions, silt, mud, so on and so forth from weathering processes, or we get meltwater that permeates the ground as groundwater. Sorry, I'm getting a lot of overlapping little lines here. Okay, and then that groundwater eventually can seep back out into the ocean, but when it does, it now may carry more ions with it. We may get precipitation going on. So for example, calcium that's picked up from groundwater may precipitate out as calcium carbonate, or may be incorporated into sea creatures that have carbonaceous shells. You do get some precipitation of those dissolved ions as sediment. Some of them remain dissolved in solution. There are other things going on. We do have hydrothermal liquids here. We have some of that coming up through magma. We have some volcanism going on, so there are other things going on there. But the main cycle here is, from ocean, lakes, groundwater, streams, into atmospheric moisture, and then back down again. Okay, so that's our main cycle that we have going on. Now, that's not anything new to anybody probably, but it's just a good thing to keep in mind because you want to know at any given point where that water is, where it's coming from. The other thing here to note is the importance of solar energy to all of this. Okay, without solar energy, we wouldn't have this evaporation, we wouldn't have this circulation going on. So we do need to keep the sun in mind as a player in this cycle. It's also a source of energy that is an input to this. So we have things that are inorganic that the energy is incorporated from inorganic sources into organic sources through these biotic species. All right, now in the next figure, he shows you a box model. And you don't need to worry about this too much. This is actually represents a zero-dimensional figure. I know it doesn't look like it in the book, but it's basically just a zero-dimensional box model. And it's showing the characteristics that play a role in water chemistry for more complex models. So the cycle that we just looked at is actually a very simplified model. It doesn't show a lot of the detail and it doesn't take into account a lot of things. The box model is just supposed to give a little bit more of an in-depth look at the things that are going to affect that cycle. Now, this box model presumes that all chemical species that are in the box are being thoroughly mixed together. So there's complete interaction between everything coming in. Okay, so the direction of flow is going in the box basically from left to right. Okay, so the supply is coming into the box and discharge coming out. Now, when that happens, different things are affecting the box coming in and out. So, for instance, dry deposition coming in. So, dry materials that are being introduced into the flow here. Snow and rain are coming in. Okay, so we have sources coming in. We also have sources coming out. So volatilization is evaporation, removal of water in that effect. Now, while this solution is in the box, we can have a couple of different things going on. We can have deposition of solid particles, so materials coming out of solution, or we can have solution of solid particles, so the dissolution or the incorporation of solid particles or ions into the model. So this is just supposed to be a section of what we're looking at that's under study. So it's like taking a small piece of the pie and looking at it in great detail. So the goal of this box model is to reflect different parameters for things such as ion equilibrium, conversions from solid to liquid and liquid to solid, and then water and ion uptake by soils. So we're looking at water, but we know that water doesn't exist in and of itself. It is in contact with land, with air. So what are the exchanges that are going on there as well? Now, we're not going to try to draw a box model or anything, but it's just a good thing to be aware of, that if we want to look at it in detail, we're probably going to need to pull a box model of what we're looking at. Are we looking at the ocean? Are we looking at a pond? Are we looking at a river? So on and so forth. All right, now in that cycle, we had all different sources of water, but where is that water? As you well know, the majority of our water on Earth is in the form of an ocean. Okay, the oceans contain 97.3% of all water on Earth. Another, about 2.1% are in glaciers and polar ice, so that's fresh water. Okay, now this is salt water, and this is fresh. Okay, as are the other things underneath here. So we're already up to about 99.4% just with oceans, glaciers, and polar ice, which, we know this one's going down a little, but again, that's a topic for another section. Okay, groundwaters, also known as aquifers. So if somebody's talking about the aquifer, and that's what we'll be talking about a little bit during our lab on Friday, what is the aquifer that we draw from? Okay, groundwaters or aquifers represent essentially the rest of the water on Earth, about 0.6%. Now, that certainly isn't completely everything that's there. So even though these add up to 100%, that's not 100% of the water on Earth. We also have, as we know, lakes, streams, ponds. We have some moisture in the atmosphere. We have some moisture in the biosphere. So we have those clouds and things like that. Those represent a mere fraction of a percent of the water on Earth. So think about, really cloudy days when it's just ready to pour rain. It looks like there's a lot of moisture in the air. It's not even a drop in the bucket for what we have. If you prefer to think of it in terms of volume, you have the volumes given up here. Okay? So you can see how these rank. If you look, that moisture in the atmosphere, all of our clouds, 1.3 times 10 to the minus, or 10 to the fourth cubic kilometers. Compare that to, to the oceans. Okay, 1.3 times 10 to the ninth. It's a factor of 5 greater, which means that this moisture in the atmosphere is 1/100,000th the amount of moisture on the complete Earth. It's just a mere fraction. Okay, so just a good idea, and here's if you prefer to look at it in terms of pictures, you can see here the amount in the oceans versus everything else. So here's the 2.1% in the glaciers and polar ice compared to the oceans. Groundwater is the box inside of there. Lakes and streams is the even smaller box. Atmosphere, the even tinier box inside of there. And these are not, as you are probably aware, to scale. Okay, but it just gives an idea of how much smaller it is to everything else. All right, so we know that the water isn't distributed evenly, but we also know the water's not static. The water that's in the ocean now is not the same water that was in the ocean yesterday, the day before, a month ago. It's moving, okay? The water that are in the lakes around here, it's not the same water. We're going to have cycling. Now, that doesn't mean that every drop of water on Earth is going to cycle to everywhere on Earth, but it is moving. So where is it moving and where is it going and how much of it is? Well, that's what we're looking at in this figure. Okay, so figure 3.1.4, and if you do have a copy of the book, this is on page 76, okay, just to help you kind of keep up with that. You can see that a majority of our water, again, is coming and going around these oceans. So the amount of water being evaporated from the ocean is 425,000 cubic kilometers. And this is, I believe, let me double check this, but I believe this is on a daily basis. Okay, so this is the amount that we have going on in a day. Now, that's the amount that volatilizes. How much is coming back down out of there? 385,000 cubic kilometers. So there's a little bit of a difference. We have more coming off the ocean than we have going back into the ocean. So where's the rest of that going? Okay, so we've got a cycle, but then some of it is getting bumped out over here. Okay, so about another 40,000 cubic kilometers is getting transported away from the ocean in terms of water vapor, in terms of clouds and movement. It's moving over land, and different things, okay, are going to cause it to appear in different areas. So movement of clouds, different things, contact across landforms, mountains, just critical mass of clouds, you're going to get some precipitation there. Okay, that's going to percolate, move down through the ground into groundwater. Some of it will eventually return to the ocean, okay, and some from the lake. So eventually, we know lakes, streams, rivers tend to flow toward the ocean. But we do get some surface evaporation from our lakes and streams and ponds and things like that. We also get evapotranspiration. So this is the water vapor that is coming from other processes like trees transpiring, just evaporation from soil, various things. That's going to put some of that back into the air. Okay, about 71,000 cubic kilometers. Okay, so you can see the cycle here, where things are going, how they're moving, and then we have this factor. So these are kind of idealized volumes that are going on. They're not quite the same from day to day, but those are just rough amounts. And what we want to do is look at what effect are people having on this cycle, because we are having an effect on that, and we're changing that. So how much are we using, and how are we using it, and where is it going? Now, I have veered off and varied from the figure that is in your book. The figure in your book, 3.1.5 on page 77, shows the average water content and water usage in Germany. And that's because the author of this book is German. It has been translated from German, so if you find the occasional odd bit of English, it's just a little bit of a different translation that's going on there. So I pulled in a figure. This is from the U.S. Geologic Survey, Water Science School, and it just shows sources and uses of fresh water in the U.S. as of 2010. Okay, so they haven't updated it since then. I do apologize, but it hasn't changed significantly since then. Now from this, you can see surface water and groundwater, what we have. Okay, now these are in millions of gallons per day. So surface water, we use about 230 million gallons of water. Groundwater, we use about 76,000 million gallons, if that makes any sense. It seems a little bit odd, but it's just a multiplier up. It's easier than talking about billions, trillions, and whatnot. Okay, so we are using by far more surface water than we are groundwater. So, what is the difference between surface water, groundwater? Surface water is lake, streams, reservoirs. We have a tendency to build dams and build up a water supply versus groundwater, pumping it up out of the ground. Okay. But even though we are using a much greater quantity of surface water, the groundwater doesn't need to be discounted. We still use a fairly significant amount, and it is very important for a lot of categories. Okay. Now, surface water is used for larger cities, industrial, and whatnot. So we can see here public supplies, aquaculture, so using it for some crops and things like that. Industrial use is another large use of surface water. Okay, mining actually uses quite a bit of water. Thermoelectric is a huge use of water in the U.S. That's about half of the water used every day is just for cooling down where we're producing electricity and producing energy. Now, you may think, oh, well, nuclear plants are going to require a lot of cooling, but our coal-fired and gas-fired plants are going to use that as well. So that is one of the issues with producing electricity is we're using a lot of water, not because we need the water to produce the electricity, but simply because we need it for cooling purposes. A lot of the energy we're producing is not coming out as electricity, but it's coming out as heat. And that's more heat than the system can handle, so we have to cool it somehow. If you drive past the Southwest Power Plant on the south side of Springfield and you see big plumes of what looks like smoke coming up, that's just steam coming up from the plant as they're cooling things. Surface water is used a little bit for domestic use, so for houses, people who are on wells and whatnot. Irrigation is a fairly large use of surface water. Irrigation's for crops. And then livestock use just a little bit. Now, if we look at groundwater, though, over 40% of the water we use for irrigation comes from groundwater rather than surface water. Also for, sorry about that, let me go back up. Used for livestock is coming from groundwater. That's a fairly large amount. Okay, domestic. Actually, about all of the self-supplied domestic water comes from groundwater. So people who are on their own systems tend to have wells. They don't tend to have, a tap into a lake or pond or something like that. Public supply, it's actually a fairly large portion of that. A little bit of aquaculture, a little bit of industrial. About an equal amount for mining comes from groundwater as surface water. Thermoelectric, very little coming from ground sources. They tend to use reservoirs there. Okay, and then the livestock here we talked about a little bit. All right, now we've already mentioned that the water isn't by itself in a vacuum. There are interactions between land and water. And so environmental science does not exist simply as one branch of science. It has to use methods and data from several different branches. So for example, hydrology is kind of the study of water. So we're looking at transpiration, evapotranspiration, we're looking at runoff, hydraulic runoff, so that's just the mechanics of the runoff of the water, flow rates of streams and rivers and so on and so forth. How do we measure these things? How do we look at them? Well, we need physics to do that. We need to know things such as the amount of energy that's coming from and going to the water. We need to know something about erosion rate. So what's the amount of interaction or interface between land and water? What is the microclimate that we're in? What is the temperature that we're in? What is the sedimentation rate? Are we looking at streams, lakes, or oceans? What kind of soil is around it? How quickly are we going to erode things? How quickly are we going to deposit things? And then the idea of silting up. And silting up is the buildup of silt in lakes, rivers, streams, things like that, where as you reach the mouth of it, you're dropping the load basically. It's picked up all of this material, and then it eventually drops that, and silt builds up to the point where it kind of chokes it off or moves it. So silting up is important. Now these are all mechanical processes that are going on. So physics, we need to look at the mechanical processes. But there are processes going on that are beyond mechanical processes. They go into the chemical processes. So that's going to be the chemistry of both the soil and the water. We're going to look at things like the rate of food cycles that are going on here, so material cycles. We're going to look at the equilibrium that occurs between soil and water. Okay, so where's the exchange going on there? We're going to look at things that change pH. pH is a huge one here. We're going to look at chemical weathering. So what are the materials that are going into solution? What are things that are oxidizing? What are things that are reducing? What are things that are forming? So here's the redox. What are things that are forming complex ions? How are these various ions interacting with one another? Organic matter, how is that affecting everything going on here? So we need to keep an eye on that. And as you've probably already guessed, that's going to be our focus for this semester, is looking at those chemical interactions. We certainly will use the physical and next the biological, but our focus will be on the chemical. And of course, you've got to look at the biology, because again, this is not an inorganic system. It's an organic system. We do have life going on here. We have biomass. We need to see how those are interacting with and affecting the water. So we have things like eutrophication, where we're looking at how we reach a point of balance of nutrients. We're looking at the production of different organisms, so levels of nutrients, how well those organisms can produce or reproduce in a system, how ecologically sound our system is. Okay, do we have niches for those life forms? Those are the kind of things. Do we have monocultures? So do we have, a biome in which one particular life form is going to exist and thrive, or is there a mix of those? So we want to kind of keep an eye on how all the different aspects affect our interactions going on in the water, in the land. In addition to looking at the interactions between the different branches, we want to look a little more at the idea of a food chain. So looking more in the biology end of things. So you're probably familiar with the idea of a food chain, but let's look at it in a little more detail. Now, a food chain is a cycle, so it doesn't really have a particular starting point, just like a circle doesn't have a start, but we're going to kind of start. Oops, sorry, I keep losing. Which way do we go there? Okay, there we go. Give me my pen back. Okay, so we're going to start at the inorganic material end of things. The reason we're doing that, inorganic material constitutes a large portion of material on Earth, so we have soils, silts, different inorganic species that are food poor. They are not in the form that can be used for energy by living beings. So how do we get the materials that we use from these inorganic materials? Well, this is where light comes in. So we know that there are certain species that can use light and convert it into a stored organic food energy. In particular, phytoplankton. Again, we're focusing on water, so there are plenty of things on land that can do that. We have plenty of plants and trees and things, but we're focusing on the food chain in the water. So we have phytoplankton in the water. So little simple beings that take light and convert it into a stored energy. We're taking a kinetic form of energy, converting it to a potential form of energy. Aquatic plants can do this as well. So they're going to lock that up. The aquatic plants have to have an input of inorganic material from salts and nutrients in the soil, as well as from the light. The phytoplankton use pretty much just the light. Now the phytoplankton are taken up by zooplankton. So simple beings in the ocean, different planktons that are a little more in the animal kingdom there. So they consume the phytoplankton, and then those zooplankton offer a nutrient source, a food source, to a variety of plant eaters. So things like fish, crabs, mussels, worms, anything that you've got in there can consume those zooplankton. Okay, then you've got the meat eaters who come along and eat those plant eaters. Okay, and eventually you get to the top of your food chain in terms of your meat eaters. Now, how do we then cycle it back? Well, we have to have the detritus. So we have excrement coming from both the plant eaters and the meat eaters. We have the organic material being returned when these die and go back down. So we get a buildup of detritus, and then the bacteria go to work and the deep sea fauna go to work, and they break down this detritus. This is what they live on, and they recycle it back into these inorganic materials that can then, and the deep fauna can go back into the plant eaters, but we can have, bacterial breakdown into salts and then back up again. So that's how we keep our cycle going within our water. And this example could be in the ocean, it could be in a lake, in a stream. Every one of them has sort of their own unique little food chain and their own species within that, but the basic idea is going to be the same there. You're going to have the same essential players in any one of those food chains. Now, it's a little bit of a bigger story when we look at the material cycle in the ocean or the seas. So when we have sea-going materials, we want to look here, we're following here the flow of carbon atoms. Okay, we've already mentioned several times carbon species play a huge role in our water chemistry. We're carbon-based beings. We have inorganic forms of carbon. We have organic forms of carbon. So what's the interchange between those? Okay, so the food chain we looked at earlier would be more likely for a shallow body of water. So things like lakes, ponds, streams, rivers. This is going to be the division that you'll see when you have a deeper body of water, a sea or an ocean. So when you have this, you have what is known as the euphotic zone, right here, which is the zone in which light basically can penetrate, where things can depend on light in order to carry out that cycle. So it's photosynthetically active. It's enough to carry out photosynthesis. Now, our carbon species are coming in various different forms. So the flow of carbon is coming in as various carbonate and bicarbonate species. We've got dissolved organic carbon, DOC, right here, and we've got particulate organic carbon. Okay, so DOC is dissolved, and then POC. These are terms that you'll see often in dealing with water chemistry. Okay, so particulate. And that's just telling you whether you're dealing with an ion. So dissolved organic carbon is generally going to be in an ionized form. It's going to be suspended in solution. The particulate, and I'm sorry the handwriting is so bad, it's really hard to write on the screen with a stylus. But that is particulate organic carbon. Okay, so that's going to be still in particulate form over a certain size. And so we've got a flow coming in of a certain amount of carbon here. We also have carbon coming into our water and ocean through the absorption of carbon dioxide. And if you have been anywhere besides under a rock for the last 10 years or so, you should probably be aware of the importance of carbon dioxide to us as a species right now. Since carbon dioxide is implicated as one of the major players in global warming and global climate change, whatever you want to term that. So CO2 is a huge player here. You can see we have about 435% of the flow of carbon coming from this. It's huge, and it's probably a little bit bigger than that by now. But the ocean and the sea is a huge sink for carbon dioxide. It absorbs a huge amount of carbon dioxide. Of course, it also releases a pretty large amount of carbon dioxide. You can see the difference here. So 435% from CO2 and another 2.2% of carbon coming in, about 437 versus 433 coming out. So there's only about 4% of that carbon that's getting locked up in the system. Okay, so the carbon species are coming in, and they tend to form in the water as dissolved carbon dioxide, also known as carbonic acid, or the hydrogen carbonate ion. Now, if it's been a while since you had general chemistry and you've forgotten all those wonderful polyatomic ions that we made you memorize, you probably want to go back and take another look at those, especially any of them that have carbon in them, because you're going to be seeing them over and over again. They do appear a lot in environmental chemistry. Carbon's out there. All right, so again, we've got our cycle here. You know, we've got our planktons, and we've got our bacteria, we've got our animals. So we've got our whole series here, just like we talked about. But now, when you get to a certain point, you've got the light coming in, it can penetrate, but it only goes so far, and it reaches a point in the deep sea where none of that light's getting through. So you don't have any photosynthesis going on. So you've got a completely different cycle here. And that occurs at this point here where R equals P. Okay, and R stands for respiration, P is photosynthesis. So up here, you can have photosynthesis going on. Below, no photosynthesis, we rely on respiration to keep that organic matter and to keep that carbon going through there. So the dead organic matter is falling to the bottom of this large body of water. Okay. And now some of it is going to get incorporated as the particulate organic carbon, so solid organic matter. A little bit of it just falls out, so you lose about 3% completely. Some of it cycles back up. It gets stirred up through ocean currents and whatnot, and brought back into the photosynthetic zone where it can be put back into the cycle. You do have a certain amount of the dissolved organic matter, okay, that can be used by creatures that live down here. There are certain types of bacteria, certain animals that can live at these depths, and they can cycle through this dissolved organic matter and the particulate organic matter. And then eventually we lose a certain percentage of it as calcium carbonate, as limestone. Okay, so if you're not familiar with calcium carbonate, you may know it better as limestone. Where does limestone come from? Well, it's usually precipitated out from these creatures. They learn how to use the carbon that's in the water, the carbonate species, and they build themselves calcium carbonate shells. So things like oysters and mussels, bivalves, any of those sort of things. Right, so a little bit of a different system for the deep sea versus the surface waters that we have, the shallower waters that we have going on. All right, so what is the human factor in all this? Well, it's very interesting, I think, in this book that, at least in this chapter, he doesn't touch on it very much. It's a very short section that he has. It's obvious that we do have an effect on the water cycle. So you can see from this figure, I'm not going to go into detail, but from the figure that he's posted, you can see approximately where, if you assume an area has an average precipitation of about 803 millimeters per year, keep in mind the author is German, so he doesn't talk about inches of rain per year. He deals with millimeters. If you're more comfortable with centimeters, that's about 80 centimeters a year. There's 2.54 centimeters in an inch, if you want to do the math there. And again, you know, it'll change depending on what area you're in and how much water they get, but you can see the flow of where everything's going. So if we look at how we're diverting, you know, some of the surface water preparation for use in households, you notice a very small little tube here. A larger amount of that water getting diverted to industries, including things like railways, agriculture, and then a lot of our groundwater and surface water getting diverted as cooling water for electricity. Well, now that does get put back out into the atmosphere, eventually back to the ocean. So we're just kind of borrowing it. What we have to worry about, though, is what happens to it in the meantime. Okay, so we're just borrowing the water. We tend to put it back out. It's not like we're removing it from the system, but what we are doing is introducing things into the system that weren't there before. So that is our big issue with the human factor, is how well are we cleaning it up and getting it back to the way it was before we put it back out there. Sometimes we do a really good job of that and sometimes not so great, but it does have a cumulative effect. In higher concentrations in some areas than others, but obviously eventually that's all going to spread around. So we need to keep that in mind. That's something we'll deal with more a little bit later in other chapters, but keep in mind that the lab that we are doing on Friday is dealing with water quality. And so when we talk about water quality, really what we're looking at is how well are we doing as human beings in getting our stuff out of the water. Okay, that's what we want to focus on there. Now, we're not the only ones affecting the water cycle, and the animals aren't the only ones affecting it. Plants, vegetation definitely has an effect on this as well. Now, this, you don't need to worry about all these variables that are in here. Basically, it's just the idea that you can measure the effect of vegetation on the water cycle. So you can actually work out formulas to look at how different species are going to affect the cycle of water through there. You can read more about that. I definitely advise you to read section 3.1.10 on page 82. I will tell you that he is a bit incomplete in that. He borrows a formula from someone else, and he does not completely explain all of his variables. But you can read through it and at least get the idea that you can work out very complicated formulas to measure how vegetation is going to consume water and how it's going to uptake. That may not seem like a big deal if you're looking at just one tree, but if you're looking at agricultural chemistry, if you're looking at the effects of agriculture on the environment, this can become a huge thing because you have certain species that may have much more of an impact. This side of the uptake of water may be much larger than the output of water. So basically, all of these variables, what you're looking at is water in and water out, and making sure that they stay somewhat balanced, that we're not removing too much of the water and locking it up from a local cycle. Now, if anyone is looking at agriculture and they're interested in knowing, knowing more about this, I would be happy to get you more information on this. But for now, again, don't worry about the variables. Just realize that, you can do that. You can look at the impact that certain types of vegetation are going to have on your water cycle. Now, the next section is one that you do want to pay attention to. This is known as a PHPE, or a Pourbaix diagram. If you've never seen one of these before, but you've seen phase diagrams, these are very similar to phase diagrams, where you're looking at how something changes phase based on temperature and pH or electric potential or something like that. And now this is the Pourbaix diagram for water with atmospheric influence. So we're kind of looking at how we cycle through various forms here. Now, things to note here. You're probably familiar with pH, okay, the potential of hydrogen in something, and it's just the, remember, negative log of the hydronium ion concentration. Okay, H3O plus. You may see it as just H plus, H3O plus, either way. So that's your pH. Well, PE, anytime you see that P in front of it, it's just the log of something. So PE is the negative log of the electrochemical redox potential. And if you don't remember what this is, the redox potential, remember half reactions. So if you've looked at redox chemistry, you know that you have something being oxidized, something being reduced, electrons are being gained by one thing, electrons are being lost by another one. That's what we're looking at. So how's the flow of electricity going on here? Okay, so this is my PE up and down here. So there's my electric potential, and here's my pH, my concentration of hydronium ions. Now we know from pH, the lower the pH, the more acidic something is, the higher the pH, the more basic, and we've got our neutral right in the middle. Okay, so with PE, the higher it is, anything from about 5 and up, the more oxidizing it's going to be. Okay, and so if you remember your oxidizing and reducing, depending, if you may have heard Leo the lion goes grr. So if it loses electrons, it's oxidized. So anything from about 5 up is losing electrons, and gains electrons, it's reduced. So anything from about 0 down is being reduced. It is gaining electrons, okay? Or oil rig, if you know that one. So there's our cutoff right there. Now notice you've got some different areas here, and you've got this area from about 0 to 20 PE, down at 0 pH, and then it goes from about 5 down to a negative 15, up here at pH 14. So this light blue area. Now that area is going to be the one that's of a little more interest to us. That one is going to represent sort of our equilibrium phase that we have. That's where things that are cycling through the atmosphere tend to fall. Now, you can see, though, that there is sort of a break here. We have things in this area such as pit water, fog, rain, streams, oceans, bodies of salt water that get aerated, that get churned and turned over, tend to be a little more toward the oxidizing end. And then you have things, so these will tend to be the things, you have oxidation going on there. So you're going to get this breakdown, this loss of electrons. Okay, and where is that going to end up? Well, down here toward the lower end of this range, we have things like marshes, wet soil, groundwater, salt water, things that are loaded with organic matter, peat bogs, anything like that. Those tend to be a little more reducing. So it's a different environment there as well. And we will be revisiting these Pourbaix diagrams, this one in particular, to kind of look at how different chemical species, carbon in particular, but other chemical species, how they're affected. So whenever you're measuring water quality, the things that you're going to measure are going to be things that tie into this. So we will definitely be measuring the pH of water. We will be measuring conductivity to relate to the electrochemical potential of that water, because we want to know where it falls within this range and what effect then those characteristics are going to have on the other chemical species that are in that water. You'll tend to see different species, obviously, in a more reducing environment than you're going to see in an oxidizing environment. So you can tell something about the health of a body of water if it's one that's normally up here in this range and then suddenly it starts losing those characteristics. You may see a drastic change in the environment that you have there and in the species that are actually able to exist in those environments. So you can use it as a way to kind of take the temperature of a body of water and measure its health. All right, I know I keep harping on this, but carbon species in bodies of water. This is where we're going to kind of end up with this section. There are going to be thousands of different carbon species in water at any given time, but you can break them up more or less into two categories, inorganic or organic. So the inorganic versus the organic, different types, and the organic is going to be a much larger category than the inorganic, but very important to us is the exchange of carbon species between these two, between the organic and inorganic, and again, it's kind of based on photosynthesis. All right, now when I talk about inorganic species of carbon and water, the primary ones we're looking at are going to be carbonate ion and hydrogen carbonate. Again, you got to go back and look at those polyatomic ions. And then also carbon dioxide that's dissolved in water. Now, when you dissolve carbon dioxide in water, it just exists as dissolved carbon dioxide, but sometimes you'll hear people refer to this as carbonic acid. Okay, so carbonic acid is actually just when you take water, H2O, and you dissolve carbon dioxide in it, CO2, you could theoretically get H2CO3. Okay, this is what is known as carbonic acid. But notice I've drawn a double arrow. That means that it's in equilibrium, and this equilibrium tends to go very much in favor of the reverse reaction. It tends to want to go back this way much more than it wants to go toward carbonic acid. So even though a small amount of this species will exist in water, it's primarily these two species, but this still has an acid effect. You'll still get an acidic solution. So you know that from drinking soda. That's what soda is. It's carbon dioxide dissolved in water, and you know that soda has sort of a tang to it. That's indicating that it's an acid. Okay, so we'll be looking at it just in terms of dissolved carbon dioxide, but you can think of it as carbonic acid if you want, as long as you realize CO2 is what you're really looking at. All right, so when we look at our inorganic species, we come back again to our dissolved organic carbon versus our particulate organic carbon. And those are going to be in differing amounts when we look at our carbon species in water. So for example, depending on the body of water, if you look in the ocean, dissolved organic carbon is about 0.5 milligrams per liter in the ocean. Versus the particulate organic carbon is only about 0.005. So the dissolved carbon is a factor of 100 times more than the particulate carbon. So most of the carbon you've got in the ocean is going to be dissolved. And that's a good thing because that makes it available for all of these species that build these hard shells. When you look in a river, you'll get about anywhere between 1 to 10 milligrams per liter of dissolved organic carbon, versus only 1 to 2 milligrams per liter of the particulate organic carbon. So rivers are fast flowing, it tends to keep it dissolved a little bit more. Okay, groundwater and rainwater, you may only be getting, and we're not going to look at the particulates there, but you know, the dissolved organic carbon drops pretty significantly from the river system. It's only about 0.5 to 2.5 milligrams per liter, whereas ponds that sit and sort of stagnate may have a lot more. They can sort of have time to let that dissolve, 10 to 50 milligrams per liter of dissolved organic carbon. So a lot of carbon moving around here. Now, I'm not going to go into detail on all this, but you'll want to dig in a little bit. Just make sure you kind of understand the movement and flow. So you're going from your inorganic carbon down to your organic species in here. Sedimentation is going to pull that back out again, so you're going to get calcium carbonate, which calcium carbonate can be considered to be an inorganic species as well, but generally speaking in chemistry we consider calcium carbonate to contain the carbonate species, so it's kind of the same thing. So that's inorganic. And then you've got your organic carbon in your sediment. Now you can also get things like methane gas. So if you're familiar with that idea, you know that the oceans are a huge trap for methane gas, which is actually a very strong greenhouse gas. So we don't want a lot of methane in our atmosphere. We do want to keep that locked up. So we have to keep our cycle in balance so that we don't suddenly shift everything this way and then up where we release a lot of methane out of our water. Okay, so carbonate species in water. We'll go ahead and stop this section here, and then in the next section we're looking at 3.2, we're going to look at the chemistry of some other different species in bodies of water. So we're going to look a little bit beyond carbon, but you'll see that carbon sort of becomes a player for all of these other species as well. They don't really exist without that carbon in solution there. But we'll look at things like how sulfates and sulfites are in solution. We'll look at some ammonium compounds. We'll look at some nitrate species in water, and we'll see how those come into play with the various roles of water in our environment.